Hello, welcome to the sixth and final lecture in the Oxram Robot Arm software lecture series. Today we're going to be looking at state machines and their integration in ROS. So today we're going to be looking at what state machines are and what Smash is as a tool for creating state machines. We're going to make a simple state machine in Python using Smash. We're going to then make a slightly more advanced state machine and learn how to pass data between the different states in the state machine. And finally, we're going to use a state machine as part of a ROS system. So we'll be calling ROS services and actions from the state machine, basically bringing together everything that we've learned in this lecture series so far to finish off the lecture series. Now, before we begin, just a reminder for the GitHub repository. So you can find these lecture slides and all the example code. I recommend having all of that on hand as you go through these lectures. Now on to the lecture itself. So what are state machines? Finite state machines are abstract machines that can be in exactly one of a finite set of states at a given time. So the state machine can transition between states depending on the outcome from the current state. And when they are initialized, they start in the start state and then eventually finish off in one of the possible end states from a discrete set of end states. Now, let's have a look at the diagram to the right. This is a state machine for a robot that's locating a user. So you would start in the init state, and then you'd transition to get robot pose. That's the next state. And then you'd eventually transition to plan path, and so on and so forth. Yeah. You can kind of think of it like a kind of like a flow chart, as you know, if you want to visualize how the robot transitions from state to state in this state machine. Now, the finite state machine algorithm works as follows. With the inputs provided to the current state, you carry out the behavior defined for that state. So, for example, you move the arm to a target position. Then you observe the results from the behavior. So did the arm reach the target, or did it maybe fail? You then use these results, success or failure, or maybe a more complex set of results to choose the outcome of the state. So maybe success or failure or whatever. And then depending on that outcome, you then transition to the next state. Perhaps for the success outcome, you transition to the next state in the planned behavior of the robot. So maybe you pick up whatever you moved your arm to, or if you failed, maybe the state machine will take the robot back to an earlier point in the state machine and repeat the process and try to achieve success in the next time. As a simple example. So what's Smash then? So Smash is a Python library used to create finite state machines. It's very useful for rapidly creating complex robot behavior. And while it is ROS independent, fundamentally, there is a Smash ROS package that allows you to integrate ROS functionalities into your state machine. So, for example, there are dedicated templates for state machines that constitute ROS action clients or ROS service clients, rather than having to manually build these things. And we're going to be using Smash to create the behaviors for the robot arm, or you could use it for any sort of behavior that you want to code up. So to illustrate these ideas of state machines, we're going to start off with a very simple example. We're going to make the state machine shown in the diagram on the right, where we just transition between the states foo and bar a few times before finishing off in an end state. So here we have the code for the example state machine simple. You can find this in the GitHub repository. I recommend typing this out yourself, but you should refer to the code when you do so. So let's have a look at what's going on here. So we first import ROSPy, then we import Smash. This isn't actually required, this import, but we will be using it later, so I included it anyway. because it will provide functionality specific for ROS with Smash, which we'll look at later. And with Smash, when you're defining states, you need to define the class structure for that state. So first of all, we have to define state foo in the diagram. So looking at by comparison to the diagram that I showed earlier. So class foo and then smash.state, and then we've got the initializer here. So this runs when we first initialize the state, when we instantiate an object of this class, and we're defining what outcome. We're defining a state here. So smash.state initialize, and then we're saying what outcomes there are. So if you look at the diagram, there's two possible outcomes for state foo: outcome 1 and outcome 2. And there's also this counter. So this is what I was referring to. This relates to what I was referring to when we were looking at OOP with ROS actions. So this self counter will be a stored variable in foo state objects. So that's some data stored within as a field within the class. And when you're defining the class structure for a state, you also need to define the execute method. So here we first say that we're executing state foo in the log info, and then we check a counter, because what's going to happen is the counter is going to increment every time we go back to state foo, and for the first few cycles, we're going to choose outcome run. So you return the outcome that you want in your execute function, depending on what happens in execute. So when the counter's less than 3, return outcome 1. So that means that will be that's our outcome for the state. Otherwise, once we've gone back and forth between foo and bar a bit, we're going to choose outcome 2, and that will do something else. Now looking at bar's a little bit simpler, because there's only one outcome. If you look at the diagram, there's just outcome 1 for bar. So in the initializer, we just initialize it with only outcome 1 available. And then in the execute, it just says it's executing state bar, and then it returns outcome 1, which means that we're going to inevitably transition back to foo. Now, how do we actually define these transitions, and how do we add these states to a state machine? So that happens in the main body of the code. So those were the class definitions for each of the state. Now in the main body, we initialize the node for a ROS node, as we always do. And then we set up a state machine here, a state machine object. So SM, so this is our object here, smash.statemachine, and outcomes equals end here means that end is the only possible final outcome for the state machine. So that's the final state, really. The end state, the end outcome for the state machine. Now what we do is we do something called opening the container. So in this section, we add states to the state machine structure, and you do it one by one. So for example, we're first going to add foo. So we add foo to the state machine, and we're going to say that if the transitions are outcome 1, if we get outcome 1, then we're going to transition to bar. And if we get outcome 2, we're going to transition to end, which will end the state machine. Meanwhile, with bar, the only transition is if we get outcome 1, we're going to go to foo. Now note that we say the names of the state, and then we say what the class is, because we defined foo and bar up here. But these are classes. Remember, these are blueprints for an object, but you can instantiate multiple objects of a class. So what we could actually have is a state machine foo1, foo2, foo3, etc., where we'd be calling them different things here, but we'd always be using this class constructor. Now, and we could do the same for bar. We could have bar 1, bar 2, bar 3, bar, I don't know, we could name it whatever we want. But again, we'd have to use the bar constructor here. But the idea is this foo and this bar are instances of the classes that we've defined. So once we've finished defining the structure of the state machine, we then execute it. So outcome equals sm.execute, and then that will just play out the state machine. So we will test the state machine now. Okay, I've got a terminal up here. I haven't made a launch file, so I'm going to have to do this the manual way. So I'm going to have to first run rustcore. So rustcore is running in the background, so we can start doing Rust stuff. And now we're going to run the state machine. Rust run tutorial scripts. Remember, you need to have given permissions, as always. Example sm. Simple. Apply. There you go. And it all happened instantly because we never set a delay for anything, you know? It's going to transition to the state machine as fast as possible. If you want to see it go from state to state and transition, you'll need to define, you know, the rate at which it will transition. So maybe you'd have to put a pause, or like, so r.sleep is what we've used in the past. But we can have a look at here what's going on. So state machines starting an initial state foo with no user data. We'll get into what user data is in a little bit. Now, executing state foo. State machine transitioning from foo, so because we got outcome 1 to bar. So now we execute state bar, foo, and then it goes back and forth a few times until we exceed the counter. So eventually we say executing state foo. Well, the program says executing state foo, and then it chooses outcome 2 because we've exceeded the counter. So state machine terminating foo goes, you know, so outcome 2 means that we enter the end state. So the state machine terminates. Yeah, and that's a simple state machine in Smash. So in Smash, you can provide user data for the state machine. So user data is a set of variables global to the state machine, and it can be used to pass data between states. So you can even access the user data directly from the state machine once you finish the execution. So you can think of it as like output variables from the state machine once the state machine has concluded its execution. And also, you know, one state can alter user data or read from user data, and then the other state can do the same, access the same user data maybe. So for a state to be able to read or write to a variable in user data, you'll have to have it defined as an input key and an output key, respectively. So we're going to demonstrate how this works by implementing this slightly more advanced state machine. And what we're going to do is we're going to log. So, okay, let's first go through what the state machine does. So we're going to start in state A, and there's a chance that each state A, B, or C will fail. So I think I made it a 50% chance of failure at each state. Yeah, I did. So you know, you could transition to A, and then success, then B, and oops, okay, transition to failure, and then you're going to go all the way back to A again. If you look at the diagram, and what we're going to do is each time we transition to a state, each state's going to have a counter that records when we've transitioned to it. And once the state machine finally terminates, we'll be able to read from each of these counters, which will be, you know, take the form of user data. We'll be able to read and see how many times we went to each state. So here we have the code for the advanced state machine. Again, we're importing RustPy and Smash. And we're now going to also import random because, you know, we're going to have these 50-50 success failure probabilities. So we'll use random to do that. So let's have a look. So we've actually defined a class for each state, but yeah, no, actually you would need to. I was wondering whether you could just define a generic state class and then instantiate states A, B, and C, you know, as different object instances of that class. But I've realized that wouldn't really work for this particular situation because we have to define, as we'll see in a second, we're going to have to define a different output key for each state A, B, and C. So that means we've actually had to define these classes. We've had to define the states in different classes as opposed to all three states using the same class. So again, so state A, got initializer. Okay, so we've got the outcomes, success and failure here. And what's here is output keys. So output keys equals A count. So this is going to be a counter for how many times we, you know, transition to state A. And in the execute, so we execute state A. So we're going to sleep for a second here. I defined R somewhere? Oh, okay, yeah. So later on, I'll define ROS-Pi rate. So this will correspond to ROS-Pi rate 2. Sleep for 1 second. Okay, this would actually sleep for half a second. So I'm gonna change that to 1 so it's correct. No, it'll take too long. I'm going to 1/2 second. There you go. If our rate's 2, hopefully that makes sense because our ROS-Pi rate means 2 hertz, which means half a second. So we're going to sleep for half a second when we enter state A. Then we're going to increment the counter, and then we're going to update. Here we go. User data dot a count equals self counter, because self counter is data stored by the state. But we're going to modify this user data, which is global to all of the states. And then we're going to do random here, and it's going to make a random choice between success and failure, 50-50 chance. And then we return whatever the result is. It could be success or failure. And which one it is depends on, will then determine to which state we transition. We do the same thing for state B and the same thing for state C. It's just, we're just changing B count, A count to B count to C count, and then just saying which state, changing the ROS-Pi log info to tell us which state it's currently in. So that's the state definitions. Sorry, the class. Yeah, the state. The classes. That's nice and straightforward. And now looking at the main code, the main body. First, initialize the node. We set our rate as 2 hertz, and then we define a state machine. And in this case again, the only outcome is going to be end. Our state machine is again only going to have one outcome, but you could have a state machine with multiple outcomes maybe. And here again, we're adding each state. So A, so the name is just going to be A, but it's an instant of this state, but it's going to be an instance of state A class. So B, state B, C, state C, and then again, also for A, on failure, we transition to A, on success, we transition to B. And same sort of logic for B and C. But with C, if we succeed, we end the state machine. We also need to initialize our user data. So look here, the user data is being initialized to 0 for all A count, B count, and C count. And then we just execute the state machine. So outcome equals sm.execute. And now, so the last thing we do is we can retrieve sm.userdata because the A count, C count, B count, and C count are global for the entire state machine. And as the states, every time we transition to a state, it will modify the values in the user data. So once we finish the execution, they'll be still stored in the same places, and we can just look them up basically, and we can read out what the number of times we visited each state. So we'll test out the code now. So I've got the terminal up and ready to test. A useful thing for you might be if you want to clear out a terminal, you can just type clear, enter, and then it cleans it up. So that's how that works. So yeah, let's go ahead and first run roscore, and then we're going to run the state machine. So rosrun tutorial scripts example state machine advanced.py. So state A, B, A, B, A, B, C. There you go. Okay. Interesting. So we start in state A. Oh, yeah, and let's look right at the beginning. Sorry. So the user data it recognizes A count, B count, and C count as the fields for the user data. The things that we can read and write data from, or to and from. So we first enter state A, then we succeed, so we transition to state B, but then we fail, so we transition to A again. We then succeed and transition to B, and then we fail and transition back to A again, and then we transition to C. So we succeed and transition to B from A, and then this time, however, it's successful at state B, so we then transition to C, and then the first time we enter state C, it's successful, so it ends the state machine. And we can see, because we're reading from the user data, A count, B count, and C count We attempted state A 3 times, we attempted state B 3 times, and we attempted state C 1 time. So, as I mentioned before, Smash has an extension for us that allows us to integrate our finite state machines with with ROS functionality, like ROS services, ROS actions, that kind of thing. So what we could really do is we could actually not use this extension. We could, in the class definitions for our states, we're perfectly allowed. It's perfectly allowable to actually, set up action clients and service clients, kind of like what we were doing before. But Smash ROS provides a neater approach. So we're gonna have a look at that approach with this next example. So what we're going to do is we're going to implement the state machine on the right-hand side. So what we're first going to do is we're going to call a ROS service. And what the ROS service is going to do is it's going to ask us for a number to be squared. We're going to give it the number, and then it's going to, or it might generate it random. I can't remember, but it's going to call the square number factory to square the number, and then it's going to pass that along to the ROS action, which is then the action client is going to tell the action server to carry out that abstract task that we created in lecture 5. That's going to carry out for the number of seconds determined by whatever the outcome of this state was. So the squared number, basically. So we're going to choose a number of seconds. We're going to square it, and then we're going to make the abstract process carry out the action for that many seconds. And we actually have to define multiple end states here, because we've got succeeded, which is the one we want, but then maybe preempted if we cancel it, or aborted. So there's now has to be multiple outcomes, because a ROS action can have multiple outcomes. So here we are. This is the last piece of code for this software lecture series, and it's the example state machine ROS.py. So let's have a look through it, shall we? We're going to import ROS.py. We're going to import Smash. This time we are importing Smash _ROS. This will be used in this code, and we're importing random again. So so it turns out we don't choose the number. We're going to be randomly generating the number to be squared. We'll see that in a sec. We also need to import ActionLib, because we're going to be using actions. Now, from tutorialscripts.srv, we're going to be importing our service stuff, and from tutorialscripts.message, we're going to be importing our action stuff. This is the stuff we did in lectures 4 and 5, so hopefully this is becoming a little bit familiar, and you're seeing how this all starts to come together. Now, because we're using the more sophisticated approach, where we're using the Smash ROS library, we don't actually need to define any classes ourselves, really. We'll need to define some methods ourselves, but we're going to be using the sort of the standard approach, which we're going to see now. So we first initialize the node. So this can be example _state machine _ROS. And then we instantiate a state machine. So there's going to be 3 outcomes, as I mentioned before: succeeded, aborted, and preempted, according to the possible outcomes for the action server, for the ROS action. And then we're going to do the opening of the container. So we're going to start adding states. There's going to be two states here. So what we're first going to do is we're going to define the callback functions for the ROS service client state. So we've got the request callback. So what this is going to do, so when we want the ROS service client state to make a request, it will run this function. And, it will request equals example service. So much like this is like lecture 4 here, we're going to instantiate an example service request. And the input number, if you remember from lecture 4, we're now going to generate, it's going to be a random integer between 1 and 3. and then we're going to return the request, and then that would be used. That would be used as the request for the service, so the server, which will then square the number and then get back to us with the response. So here it is. So once the service client state retrieves the response, what it's going to do is it's going to record what the user data .service response field is. So user data service underscore response equals response .output number, and then it's going to return succeeded. This state's always going to succeed. And now what we do is we're going to use this fancy constructor to initialize the state. So smash.state machine.add ROS service. So that's going to be the name of our state. But the class, the type of state that it is going to be smash underscore ROS dot service state. And then there's a few more inputs here compared to what we've been looking at for the past couple. So let's have a look at what they are. Example services is going to be the name of the service. So, we were calling it example service 1 before, but it's just going to be example. You know what? To make sure this actually works, did I save it as... Yes, example service 1. So what this means is in order for this server to be able to accept requests from this client, we're actually going to need to change this to... we're going to have to change this to example service 1. The reason why should be very clear. It's straightforward. Of course, the type of service is going to be the example service type that we defined in lecture 4. And now we have to define the callbacks. So request callback equals the request callback that we've defined here. Response callback equals the response callback that we've defined here. Now the output keys are service response. So this is the output for the user data. So how we had input keys, and then that means that the state can read from user data. Output keys means that the state can write to the user data. I don't know if I made that explicitly clear, but that's how that works. And then finally, the transition. So the only possible transition is ROS action, because we're always going to succeed. Now for the action client, we actually have to decide. Actually, it's very similar, because we've got request and response. For the action client, we've got goal and result. And we're actually not going to do feedback here, from what I gather. I think we're not actually going to define feedback here. You could, though. If you wanted to, you could define a feedback callback. But we're not going to bother in this case. But it should be obvious how that works. So we define the goal callback. So seconds requested is the user data service response, which means that we're going to have to be able to read from this. So the input key is service response. We need to read from what the service wrote to, and then we're going to return the goal, and then that gets that's the goal which the action server receives, and then the action server processes the goal and returns the result. And now, finally, there's the result callback. So here we go. So if we succeeded, we return succeeded. And then we also have cases for preempting or aborting the action. And finally, we add the action state. So ROS action is going to be its name that we give it, but it is going to be of type smash underscore ROS simple action state. And the name of the action is example underscore AS, like it was in lecture 5, because that's what the action server is going to be waiting for. That's what it's going to be waiting for actions called example underscore AS of type example action. And then, we're setting up the goal callback and the result callback. So, these two here. So we're putting them as the two input arguments. So this is what it's going to use these. And then the input keys obviously is a service response, in contrast to where it was the output keys for the service, obviously, because the service is writing to service response, but the action is the action state is reading from service response to figure out how long the action should go on for. And then if we finally define the transition, so the three end states for the state machine, we just define the transitions there. And finally, we're going to just initialize the user data to a service response equals 0. This will obviously be overwritten as the state machine executes, but you always need to initialize all of your user data. And finally, it just executes the state machine. So let's test it out, shall we? So I've got a fresh set of terminals up now, and it's time to test. So what I'm first going to do, I'm actually going to run, because we made that launch file, right? So rather than running roscore and then loading up the servers, I'm just going to run ros launch tutorial scripts example action server.launch. So this will load up the action server, and it will also start up ROS in the background as well. So then I'm going to just do ROS run, because we didn't make a launch file for anything else. I'm just going to do ROS run tutorial scripts example service server Python. There you go. Because we need both the service server and the action server running in the background for this to work. Because the state machine is going to house both the clients, because the service client is one of the states and the action client is the other states, but the servers are separate programs that our state machine is outsourcing these processes to. So now that we've got those both running, let's run the state machine. Rus run tutorial scripts. Come on, there you go. Example state machine Rus. There you go. So we can see here both the that was quite quick, and because we didn't have feedback, it wasn't as verbose in terminal, but you can actually see it was waiting for the action server a little bit. It eventually did. Then eventually, well, actually, so first of all, it started off in the ROS server state, and then the service here received the order. So we randomly generated the number 2 in the state machine, and the service squared the number and returned it back to the state machine. Then the state machine waited for the action server, which it didn't connect to immediately, so it waited for it, and then eventually it did connect to the action server, example_as. And then you can see here the action server received the request. So action request received, seconds requested 4, what we'd expect from the service. So then it performed that action. So then there was a 4-second pause, and it returned success after 4 seconds. Now we didn't have a feedback callback set up in our state machine action client state, so we didn't get feedback being sprawled out here. But this would have been sending feedback. So if you wanted to listen into it, let's do that again, and I'll prove my point here. ROS topic. Let's first find where so we're gonna echo into the feedback. Example AS feedback. Oh no, why did I say ROS topic echo? There you go, ROS topic echo. Okay, now I'm going to run the state machine again. And here we go. We're reading the feedback, by listening into the to the feedback message that is being published by the server. So feedback is still being published. We just haven't made the state machine do anything with it. If that makes sense. And then once the action server returns success, that's received by the state machine, and therefore the state machine transitions to succeeded. So, this has brought together a whole bunch of stuff that we've learned in this lecture series. Okay, to finish off this lecture, I just want to talk a little bit about state machine design. Um, and the first thing we're going to talk about is fault tolerance state machines. So when you're designing a state machine for your robot, you need to make sure you've covered, every possible outcome in real life, even the undesirable ones. So you can't just have a state that says, inside the state, it tells the robot to move to a target, and then the next state is, I don't know, do whatever the robot's supposed to do next. Because what happens if the robot fails to move? You need to have a success and a failure, or maybe there's a variety of different outcomes that could happen. Another example, object detection. What happens if your object detection software can't find the object you're looking for? You need to be able to consider every possible outcome, to every reasonable possible outcome for the system. So you need to have fallbacks in place for when things don't go to plan. So this is fault tolerant state machine design. You're tolerant to possible failure. And when you're designing state machines, when you're designing fault tolerant state machines, the fault tolerant part will probably be the part that's the most time consuming. So here from the ROS wiki is an example state machine that's used for the behavior for a robot charging itself at a standard outlet. So each of these states call a ROS action, and their outcomes depend on the result, right? Kind of like what we just did, but the actions that are called in this example are a little bit more advanced than simply going through a timer. But look at how this state machine's built. Look at every single state has a succeeded and an aborted. And there's other states as well, actually. There's a preempted state, which all of them go to. So if you cancel everything, there's an unplugged final state as well. You can see it gets quite messy, exponentially so as you add more states, really. That is a fundamental weakness of state machines. A fault-tolerant state machine grows exponentially in complexity as you add more states. But yeah, it's really important that your state machines can deal with will deal with every outcome, and your state machine is reflective of the actual of real life. Yeah. And another thing to bear in mind is the idea of hierarchical finite state machines. So it's a hierarchical state machine is a state machine built up of state machines. So it's a state machine nested within another state machine, as shown in this diagram on the right. One quote unquote state in the state machine is actually a whole state machine in and of itself. So yeah, this helps combat this exponential complexity that I was talking about on the previous slide. And what's great is Smash provides full functionality for this as well. So if you're making a particularly big state machine, I'd really use these because they'll help cut down on the complexity. So with state machines, there's a really good resource online. It's on the ROS wiki. There's plenty of documentation on using Smash and Smash_ROS. So there's examples I've shown, I've made them, but there's many, many more that you can try out and test yourselves in order to get to grips with making state machines, getting familiar with them, and gaining an intuition for building robot behaviors. I personally really enjoy it. So I hope it is, a fun and rewarding for you as well. So in summary for today, we gave an overview for finite state machines in Smash. We created the simple state machine in Python. We tested it out, saw how it worked, and we then looked at the more advanced state machine, looked at parsing user data. And then we finally called ROS services and actions from Smash. So we integrated ROS functionality into a state machine. And that's really important, because realistically, if you're developing something with ROS and you're using a state machine, or almost all of your states are going to be calling ROS services or actions, or similar to that, because one node will be the behavior. We're dealing with the robot behavior, so that would be kind of the brain. But then other nodes will be handling all the other things, like the motion planning and the computer vision, and you'd be outsourcing stuff to those, and you'd be doing that outsourcing and communication using ROS services and actions, coordinated by the state machine. So the final homework is to just revise the content of the lecture, go over the code, and make sure you can understand what's going on with these state machines. And that's the end of the lecture and the lecture course. I really hope you enjoyed it as much as I did. I really enjoyed teaching this and showing off all these really cool things. I really hope this inspires you to develop your own code, start developing your own systems using ROS, and start playing around with robotics. Thank you for watching. Goodbye.